Day to everybody. How are you? So I hope everybody's doing well, and I'm sure that you are already overwhelmed with the requirements that you are doing, especially in your other subjects. But fortunately, under discrete math, you still have no requirements to be submitted. That's okay. We're fine with that. Don't worry, the requirements will be coming pretty soon. But for today, I would like to give the third video lecture, and I would just like to continue on with our lesson. So just a quick review for the previous two lecture videos that I have given you. We have defined what a proposition is. So it's a declarative statement that can either be true or false. So together with that definition of a proposition, we have considered the connectives. So we can connect two or more propositions together. We have our conjunction and, we have our disjunction or, we have our conditional statement, if then, we have our biconditional statement, if and only if, and of course, don't forget, we also have the negation. And then, we have also mentioned there that we can actually combine several propositions together so that we now obtain a compound proposition. So far, what we have done is, let's say we are given a compound proposition, we can actually consider the truth values for that compound proposition. And we have just limited our discussion using truth values and truth tables. Okay? Then from there, we have also mentioned that if we have propositions that will have equal truth values from our truth table, then we call these propositions as logically equivalent propositions. But I think I have only given one example for that one. So that's where I want to concentrate our discussion for today. Logically equivalent propositions. But then again, we are just limiting ourselves with our truth table, our truth values. But to maximize our time, to maximize our discussion, I would like you to please open your module to the next section, which is on the rules of replacement. So the rules of replacement are actually logically equivalent propositions. And later on, we will be using these rules of replacement to prove arguments, to prove compound propositions also. Okay? But before we can use these rules, I think it would be best for us to explain why these rules are logically equivalent with each other by simply using our previous lesson. So if you have already opened your modules to the next section, our rules of replacement, you will find there we have 14 actually, 14 rules to consider. The first rule is what we call the idempotence rule. So the idempotence rule, there are two formats for that. We have P if and only if, P or P, and the other one is P if and only if, P and P. Though you will find here our biconditional connective, this compound proposition is simply telling us that P is logically equivalent to P or P. So P is logically equivalent to P or P. So how do we show this? So using our truth table, since we only have one proposition involved, which is the proposition P. So we now have P, and then we have P or P. So we want to show that proposition P is just equivalent to P or P. And since we have a single proposition here, this proposition can either be true, this proposition can also be false, or it can be false. Now, if we want to consider P or P, so let's say we have this truth value of P, which is 1, or the truth value is true. So we have the disjunction or. So if one proposition is true, then this must be true. P or P. 1 or 1 must be 1. 0 or 0, false or false, must be false. So you will see here clearly that we have P is logically equivalent to P or P. So similarly, if you will do the second part, the process will be the same. Or maybe we can include it here. We have P and P. 1 and 1 must be 1. 0 and 0 must be 0. So you will now find here that P or P is logically equivalent to P. P and P is logically equivalent to P also. Next, the second rule there is commutativity. And commutativity, we have again two parts for the commutativity. P or Q is equivalent to Q or P. And we have P and Q if and only if Q and P. Again, our biconditional connective here is saying that the left side is logically equivalent to the right side. So like in algebra, when we say commutativity, we can interchange the position of our propositions without changing its truth value. But of course, we have to show. We can consider the first one. We have P and Q involved here. And we have 1, 1, 1, 0, 0, 1, and then 0, 0. We need P or Q. We have Q or P. So we want to show that this proposition is just equivalent to Q or P. So P or Q, we consider P first. If one is true, then this must be true. If one proposition here is true, P or Q must be true. One proposition is true. Both are false, this must be false. So similarly here, we just interchange. 1, 1 will be 1. 0, 1 will be 1. 1, 0 will be 1. 0, 0 will be 0. Again, you will find here that the truth values are equal. Therefore, we have shown that P or Q is just equivalent to Q or P. The process will be similar for P and Q if and only if Q and P. I can leave that part for you to verify. The third rule that you will find there is called the Associativity Rule. And for the Associativity Rule, we have two. P or Q or R if and only if P or Q or R. Or we can also have P and Q and R if and only if P and Q and R. So we have two parts. We can just show one and then you can verify the other. Okay. And we have three propositions, P, Q, R. So if we have three propositions, we have 1, 1, 1, 1, 0, 0. Oops. Okay, it will not fit. Wait for a while. What's happening with my screen? Let me change the screen. Let me use a fresh screen here. So we have P, Q, R. If we want to prove letter A, we want P or Q or R. And the other one is P or Q or R. So we can do this directly. So we have 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. And then here we have alternate 1, 0, 1, 0, 1, 0, 1, 0. Remember what I have said before? If we have three propositions, the first proposition, we have it into two, 4 true values and then 4 false values. The second proposition, 2 true values, 2 false values, alternate. And then the last one, alternate single values, 1, 0, 1, 0, 1, 0. Okay, so or, P or Q, P or Q, P or Q, this must be true, or R, this must be true. Did you get that? Second, P or Q, that must be true, or false. So this is already true or false, this must be true. True, P or Q, this is true, or true, true. True or false, this must be true. True or false, this is still true. True or false, true. True or true, this is also true. And then true or true, 0. Sorry, this is false or true, this must be true. True or false, this must be true still. False or false, false. False or true, true. False or false, false. False or false is also false. Okay? Next. So we get Q or P. Q or R. Q or R, that's 1. Then P or, so that's 1 or 1, 1. Q or R, that's 1. 1 or 1, 1. 0 or 1, 1. 1 or 1, 1. 0 or 0, 0. 1 or 0, 1. 1 or 1, 1. 0 or 1, 1. 1 or 0, 1. 0 or 1, 1. 0 or 1 is 1. 0 or 1 is 1. 0 or 0 is 0. 0 or 0 is 0 or false. So you will again see here that this column is exactly the same as this column here. Therefore, we have shown associativity. Next, we have the fourth one, which is called the De Morgan's rule. And for the De Morgan's rule, we have two parts again. Letter A, not P or Q is equivalent to not P and not Q. Okay? Or the second way we have the De Morgan's is not P and Q is equivalent to not P or not Q. So it's like we're distributing the negation to the two propositions. But just be careful. Look at this. What happens? What happens as we distribute the negation? It's true we have distributed the negation to the two propositions P and Q, but look at what happened. From or, it became an and. From and, it became an or. Okay, two propositions are involved. P, Q. So 1, 1, 0, 0, 1, 0, 1, 0. Let's look at letter A. We need the negation of P or Q, and we also need not P and not Q. So I hope it will be fine with you if we just do some sections mentally. Let's go here. Inside the parentheses, we have P or Q. This is a disjunction. Therefore, if one proposition is true, this must be true. Then whatever value we get here, we negate it. First row. 1 or 1 will be 1. Diba? True or true will be true. But we negate that. So when we get 1 or 1 is 1, we negate it, this becomes false. 1 or 0 is 1, we negate 1, that becomes 0. 0 or 1 is 1, we negate 1, that will be 0. 0 or 0 is 0, we negate 0, this must be 1. We must also get the same thing here. This is now a conjunction. So conjunction, both must be true. Both must be true so that the entire proposition will be true. Okay, but remember, we're negating P and we're negating Q. We negate P, this becomes false. We negate Q, this becomes false. False and false will be false. We negate P, this will become 0. We negate Q, this will become 1. 0 and 1 will be 0 because it's an and. It should be both true to be true. This becomes 1, this becomes 0, 1, and 0 will be 0. 0 becomes 1, 0 becomes 1, 1 and 1 will be 1. So you will find again that these two columns are equal. Proving now the De Morgan's rule. So that's the fourth. The fifth rule of replacement is the distributive property. Actually, 5 and 6 are similar. In number 5, you will find there the distributivity of the conjunction and over the disjunction or. While in number 6, you will find there the distributivity of our conjunction, or our disjunction or over our conjunction and. So let me discuss number 5. And in number 5, we have P and Q or R is equivalent to P and Q or P and R. It's quite long. I hope this will fit in our screen. We have three propositions, P, Q, and R. And let's write down now our truth values for our propositions. 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, and of course the last alternate 1, 0, 1, 0, 1, 0, 1, 0. And then, do you want us to go straight to this one? So we have P and Q or R. Okay, let's try to figure that out. P and Q or R. Of course, we'll start with Q or R. Or, if one proposition is true, this must be true. Then, this is a conjunction. Therefore, both must be true for the final truth value to be true. Okay, Q or R. This is true. True and true. This must be true. Q or R. This is true. True and true. This must be true. Q or R. True. True and true. True. Q or R. This must be false. And this must be false. This is true. 0 and 1 is 0. This must be true or, and then we use 0 and 1. This must be 0. 0 and 1 is 1. 0 or 1 is 1. 0 and 1 is 0. 0 or 0 is 0. 0 and 0 is still equal to 0. Remember, pag and, dapat parehong true. And then, for the right side, we need P and Q or P and R. So, if you want, pwede namang isa-isahin pa yan. P and R, get a column for that. And then, you have P and R. O, sige. I'll introduce another way for you to be able to write down. If you like, you can put a column here. And then put another column here. And then this column here. Okay. So that you'll not get confused. Let's first consider P and Q. P and Q. P and Q. This must be true. P and Q. This must be true. 1, 0. P and 1 and 0. 0. 1 and 0. 0. 0 and 1. 1. 0 and 1. 1. 0 and 0. 0. 0 and 0. 0. Now for P and R. 1 and 1. 1. 1 and 0. 0. 1 and 1. 1. 1 and 0. 0. 0 and 1. 0. 0 and 0. 0. 0 and 1. 0. 0 and 0. 0. And then, this column here will now be for our disjunction or considering these two propositions. Therefore, this fourth column will now be compared later on with the sixth column. If they are equal, then the propositions are equal. So we now compare this truth value here with this truth value here using our disjunction or. Or if one proposition is true, then that must be true. So 1. This is also 1. 1. 0, 0 is 0. 1, 0 is 1, 0 is okay. I think that P and Q. P and Q, that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. P and Q. So this must be 0. Sorry. This must be 0. 0 or 0 will be 0. 1 or 0 is, again, what's this? P and Q. That's 1, 2, 3. This must be 0 again. Sorry. This must be 0 again. Then 0 or 0 is 0. And then 0 or 0 is 0. 0 or 0 is also 0. So if you now compare this column with this column here, we have the same entries. 1, 1, 1, 1, 1, 1. And then all zeros na nandun. Therefore, we have shown that P, the left side, P and Q or R is equivalent to P and Q or P and R. So we have considered this here together with this column here. So that's the distributivity of the conjunction N over the disjunction R. So number 6 will be similar with that one. And number 7 in your list is the double negation. So I think that is already self-explanatory. The negation of the negative of P is just equal to P. Diba? Parang sa algebra, negative times negative is, or negative 1 times negative of x is equal to x. So let's proceed to number 8 instead, which is the material implication. And for the material implication, we have P implies Q. So this is already number 8. P implies Q is equivalent to not P or Q. So similar process. We have two propositions involved here, P and Q. 1 1 0 0 1 0 1 0. Left side is P implies Q. Right side is not P or Q. Let's consider the left side first. P implies Q. Implication, we look at the first proposition. If the first proposition is false, it's a giveaway. This must be true. If the first proposition is true, verify the second proposition. If it's also true, this must be true. But if the second proposition is false, this must be false. And then, for this column now, not P or Q. So we negate P first. This becomes 0. This becomes 0 or 1. This must be 1. This becomes 0 because we negate it, or 0, 0 pa rin. This becomes 1 or 1. That must be true. We negate this becomes true or false. This will be true. Check out this third column and the fourth column. They are equal. So that's for the material implication number 8. Okay. So we still have how many? We have 14 all in all. So we have 9 is the material equivalence. I think we have already defined this before. Remember when I have mentioned to you that P implies the biconditional statement, P if and only if Q is just equivalent to P implies Q and Q implies P. I have discussed this when I have shown you the truth values for the conditional statement. So that's just the same thing there. And then for the exportation, number 10. Number 10, exportation. What do we have? P and Q implies R. And this is equivalent to P implies Q implies R. Again, remember, we're just using here our truth table to verify. There are 3 propositions here, P, Q, R. Okay. If there are 3 propositions, first proposition, 4 na true, 4 na false. Second proposition, tig-2. Third proposition, alternate. So, that's always our pattern para mas systematic tayo. Next, what do we need there? Nasaan na? Nasa na siya? Yun. What happened? Sorry. How do I remove that again? There you go. Next. What do we need there? We need for the left side P and Q implies R. Kaya ba natin minsanan na to? P and Q. 1 and 1. 1 implies R. Okay. I think para hindi tayo mahirapan, hatiin na lang natin. Ganyan na lang natin siya. Okay. And then, tingnan natin dun sa implies mamaya. So, ano yung P and Q? And 1 and 1. 1 and 1. 1 and 0. 1 and 0. 0, 1. 0, 1. 0, 0. 0, 0. Implies R. So, this whole thing here implies R. This becomes the first proposition. If the first proposition is false, this must be true. If the first proposition is true, we look at the second proposition. True implies R. R is true. True. True implies false. This must be false. Okay, so that will be for P and Q implies R. But my screen is small. Let's just do that separately. Excuse me. So we have P implies, what do we need there? P implies Q implies R. Okay. So, 1, 1, let me just rewrite. Values for P. That's the first. Kaya taga-apat, di ba? And then, kunin natin si Q implies R. Q implies R. Nasaan na yun? Q implies R. So, pag false, automatic true yung magiging value. So, pang ilan yun? Third, fourth, fifth, sixth. Third, fourth, fifth, sixth. Third, fourth, fifth, and sixth. Automatic sila. Kasi false yung Q. Diba? Next, true, true. So this must be true. And then, Q implies R, ha? True implies false. This must be false. And then, alin pa bang wala? The fifth and the sixth. The fifth and the sixth. Q implies R. 2, 4. Fifth and sixth. 1, 1. That must be 1. And then, of course, this 0 na yun. Kasi 1, 0. And then, we use implication. Implication, ito yung first proposition. Pag false, automatic, this must be true. Pag true, true rin dapat yung second. So, this must be true. This is false, true, and then true. Do we have the same? Yes. Okay. Compare this column here together with this column here. The second entry is 0, the rest 1. The second entry is 0, the rest is 1. So they are also equal. So that's number 10, exportation. Exportation. And then we now have number 11. Number 11 is absurdity. And under number 11, what do we have? P implies Q and oops, what happened? P implies Q and P implies not Q being equivalent to not P. There are only two propositions, P and Q. So, truth table lang tayo. We have 1, 1, 0, 0, 1, 0, 1, 0. Left side, we need P implies Q. P implies Q. Okay. So, if you like, P implies Q. 1, 1, 1, 0. P implies Q. And then, we have P implies not Q. P implies not Q. So, we negate this. P implies 0, 0, automatic. This will be 1, 1. Not Q. This becomes 0. 1 implies 0. This must be 0. This becomes true. True implies true. This must be true. And then, for the left side, we use the conjunction for these two propositions here, right? We get the conjunction. Conjunction, both must be true for the resulting proposition to be true. True, true, because both are true. This must be false. Okay. And how about what's not P? Not P. Not P, this is 0, 0, 1, 1. What are we comparing now? This column here and this column here. Are they equal? Yes. 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1. Okay. So that's number 11. And we're almost done. Are you still alive? Number 12. Number 12 is for the contrapositive. P implies Q is just equivalent to not Q implies not P. P and Q, we only have two propositions. 1, 1, 0, 0, 1, 0, 1, 0. And then, we need P implies Q. If the first proposition is false, this must be true. First proposition is true. Second proposition is true. This is also true. First proposition is true. Second proposition is false. This must be false. So that's the left side. And then for the right side, we need not Q implies not P. Not Q. Not Q. So we negate this. If this, and this becomes the first proposition, Also not Q. Or look at this. Not Q, not Q. This becomes false. Therefore, not Q implies not P will be true. Because this is false. This is false. This will now be true. Now, we get not Q, this becomes 1. Implies not P, this becomes 0. 1 implies 0 will be 0. Here, not Q, this becomes 1. Implies not P, this becomes 1. 1 implies 1, this must be 1. And they are equal. So this is now your not Q implies not P. So we have shown that that's also equal. And we're almost done. Number 13. But for number 13, we have several. And number 13 is called identity. Maybe I can just discuss a few, maybe two, the first two. Letter A, we have, what happened? Nawala yung screen. So that's P or 1 is equivalent to 1. So what is the 1 that you find there? It's a true value. Oops. it's a true value. Remember, we are using 1 for true, 0 for false. Okay, so we only have one proposition there, P. And of course, our value, true value, 1. For P, we have two possible, we have two choices only. Either P is true or P is false. And since this is true, then we have no other choice, but that will always be true. Right? Therefore, if you now consider P or 1, P or 1, P or true, 1 or 1, 1. And then 0 or 1, 1. So you will find here that P or 1, the entries are equivalent to the entries for our 1. So that's for letter A. So letter B will be similar. We have P or 0 if and only if P. What's the 0 there? That's your false value. False value 0. So P, that's a proposition, either true or false. This is a false value, so that must always be false. We want to consider P or 0. 1 or 0, 1. 0, 0, 0. So look at the result. Your P or V, 1, 0. What's your P? 1 or 0. So they are equivalent. P or V, 1, 0. P, 1, 0. P or V equals P. So you will do the same thing for the rest in number 13. Wow! And finally, we are now down to the last. And for the last one, even the note is already excited to save. Number 14, absorption. There are two. Let's just discuss the first one. We have P and P or R if and only if P, or they are equivalent. And then the next one, pag titingnan nyo letter B, pinagpalit niya lang, naging P or P and R equivalent to P. How many propositions do we have here? 2, P and R only. P and R. Good thing there are only 2 propositions. 1, 1, 0, 0, 1, 0, 1, 0. Excuse me. The left side, we have P or P and R. P and R. Both must be true. P and R. False. False. This is also false because that this will only be true if both P and R are true. And then we now consider P. So for the OR, P, what's your P? True. True or true? True. True or false? True pa rin. False or false? False. False or false? False. So, anong sabi niya rito? P or P and R is equivalent to P. Aling column yan? Let's compare this and the column of P. Are they equal? Yes. 1, 1, 0, 1, 1, 0, 0. Therefore, P ano yun? P I have considered letter B pala. Okay. P or P and R is equivalent to P. So there you have it. We have shown the 14 rules of replacement, and we have explained that These are logically equivalent propositions, and we have only utilized our truth table in proving that they are equal. In our next lesson, since we have already proven that the rules of replacement are equivalent propositions, we will now be using them later on to transform or to convert some of our propositions. So instead of just using the truth table, we can now use our rules of replacement. Okay? So for today, that will be all. I hope things are clear with you. So at least since you are given the video, you can just go back every now and then. If there is a part that is not clear, just rewind, just go back until you get it. Okay? And again, if there are questions, please feel free to ask me. Feel free to email me. Feel free to message me. So good day to everyone. Stay safe. And I'll give you again the next lesson very soon. For today, that will be all. Okay.